Hello everyone, welcome to our discussion of section 1.6 where we will be talking about limits at infinity, infinite limits, and some connection between those and asymptotic behavior of rational functions. Well, the first thing, let's look back at section 1.3, and we learned in that section that in section 1.3 that some limits do not exist, right? Such as this one. That limit of 1 over x squared, for example, as x approaches 0, does not exist. We learned this already. Now recall the reason for this. Why does the limit for this function as x approaches 0 does not exist? So let's recall the reason for that. So the reason for this is that as x approaches 0, which is the limit, or as x approaches 0, the value of the function becomes bigger and bigger. The value of 1 over x squared becomes larger and larger, but not only that, it grows larger and larger without any bound. That's the key here, without bound. Okay? So there's no limit to how large this function can get as x approaches 0. In other words, and a few of the values of x for which we calculated the value of the function, as the values of x were getting increasingly closer and closer to 0. So we had, let's draw a small table here just to get a concrete sense of what we're talking about here. Here's a small table. And we had x, so plus or minus 1, and let's make these very increasingly closer and closer to 0. So I'm just going to pick a few more like that, and finally 0.001. So you can see the x values are getting closer and closer to 0. What happens to the value of the function then? The value of the function you can calculate is 1 first and then 4. Notice as x approaches 0, what happens to the value of the function? It's getting bigger and bigger and bigger. And of course this will continue. If you pick even values that are even closer to 0, you will see even larger and larger values for the function. And there's no limit to how large this value of the function can get. Okay? Now, in mathematics, to express this kind of behavior, we have a notation for this. So you can say limit of this does not exist. That's one way of saying it. But a shorter, more concise way of saying the same thing, that the limit of this function as x approaches some value does not exist, we can also have this notation. So to express the same thing, and this is critical, so to express this kind of behavior that you see, a value of the function getting larger and larger without any limit, this kind of behavior. larger and larger without any bound, we use this notation. We say that limit of this function as x approaches 0 is equal to infinity. Now, this isn't a limit. Please remember, the limit of this function as x approaches 0 does not exist. This we know. But the way we show it is this. We show that the limit of this function as x approaches 0 equals infinity. Not that the limit exists and it's at infinity. No, that's not what we're saying. It's just a way of saying that the limit of this function does not exist. Why? Because its values are getting larger and larger and larger without any bound. So what I've boxed here is the mathematical way of saying this, in fact, that growing larger and larger without any bound. Okay, so once again, the limit does not exist, but this notation expresses why the limit does not exist, because the value of the function increases without any limit, without any bound, as x approaches some value, in this case 0. Okay, so this is the notation for saying that. So let me actually, this is such sensitive issue, so let me write this. So this is not a limit. It is not a limit. Larger as x approaches 0. Okay, so it's part of the mathematical language, but it does not mean that the limit exists. Okay. So we want to show what does this mean graphically. Let's show this graphically. What does it mean when the limit of a function is equal, does not exist because the value of the function becomes larger and larger, approaching infinity? What does that mean graphically? So let's look at a quick look at that. So that notation that we just had, this one, graphically, it translates into asymptotic behavior. So the emphasis on can. So it can, not always, but it can translate into that. So here are a couple of quick graphs for showing that. if we have our y-axis here and here, and so let's have this graph represent some function such as this. Limit of function f of x as x approaches a, and this is equal to 1 over x minus a, right? So we would expect to have a vertical asymptote, as we learned in Pre-Calculus 1, Math 126. We can expect to have a vertical asymptote at x equals a. Right? So this is x equals a. And let's put that also here. So then we can have either this kind of behavior, right, with this end exhibiting asymptotic behavior as x goes through that. Or if we had, let's say, minus, so this would be that. And then we could have another one saying limit of f of x as x approaches a equals minus 1 over x minus a. So again, we have an asymptote at a, but this time our function approaches getting closer and closer to negative infinity. So we have this kind of behavior. Nonetheless, whether we have this kind, so this belongs to this, whether we have this kind or this kind, look at the behavior at this side, here and also here. Here, the value of the function gets increasingly and without bound approaching infinity, positive infinity, and here the values of the function approach negative infinity. Okay, so we can actually express that more precisely like this: limit of function f of x. Maybe I should have called this g of x just to distinguish, because they're slightly different. This is 1 over x minus a, and this is minus 1 over x minus a. So let's call this g of x, and that one f of x. Okay, so limit of f of x as x approaches a from the left is equal to infinity. Again, this is just a way of showing with a symbol what's going on, that the limit does not exist, right? And then, of course, on this side, limit of g of x as x approaches a from the right side, right, is equal to minus infinity. Okay, so these are, again, notational way of saying, hey, the limit does not exist. And why? Because the values of the function are either getting larger and larger without any bound, or getting smaller and smaller without any bound. Okay, so that's just the graphical way of saying the same thing as the notation is saying. Okay, so, and people say, how do we read this notation? And I've made a note here in my notes, just a reminder for me to quickly mention that this symbol, so the symbol limit of f of x as x approaches a. So the way we read this is by saying, so this symbol can be read as the limit of f of x as x approaches a is negative infinity. So the way we read this is as follows, okay, and end quotation mark there. So in this case, in this section, we're going to talk about different techniques of finding the limit as the infinite limit as the x value approaches some constant, or finding the limit of some function as x approaches infinity. So we're going to look at different techniques of doing either one. Okay, so let's look at these. These are very, very important in all the calculus courses that you'll be taking. So we want to kind of categorize these in different techniques. So we're going to talk about now, with examples of course, finding the limit of a rational function as x approaches a constant value. Okay? Say -1, 2, 0, what have you. But it's some constant, x approaches some constant value. Okay? So what are some of the techniques we use to find the limit of the rational function as x does that? Okay, so first thing, simplify the rational function. This is something that we learned in, not with regard to limits, but in pre-calculus 1, and even I think to a lesser extent in college algebra, Math 124, we did a little bit of this. We simplified rational expressions, right? So simplify the rational function. That is, if possible. If it's not possible, then we don't worry about it. But if possible, that's the first thing we do. We simplify the rational function as much as possible. Then apply the limit. And let me quickly add that if the rational function cannot be simplified, then apply the limit and note approaches. And of course, we'll do examples so you know exactly what this is talking about. So let's jump right ahead with an example. Suppose we want to find the limit of a rational function like this as x approaches some constant, let's say -3, from the right-hand side. Okay, so this is our question. Well, one quick look at this, I'm sure you can see that we are not able to simplify this rational function more than it already is, right? So we go ahead and apply the limit right away. So what will we get? We will get So if you apply the limit right away, what will happen is the numerator, so this is what we mean when we say apply the limit and note to what value the function approaches. That's what I'm doing now. Numerator here, if you plug in this, if you apply the limit here, or approach -3 from the right, let's say -2.99, -2.995, -2.999, so that means approaching -3 from the right. So the numerator approaches some negative value, right? Approaches a negative value. You don't have to find what that value is. You just need to make a note of what is it approaching. In this case, the numerator approaches a negative value. So what happens here? If you do the same, if you plug in -3 and approach -3 from the right with the values that I just said, some examples of, or -2.99, -2.995, -2.99995, such and such, this value gets increasingly approaches 0. So approaches denominator approaches 0. So you have a numerator that is approaching a negative value, say let's say -0.9 or something, right? Or -0.995 something, and then divided by a value that is increasingly approaches 0. So of course this is going to lead to -infinity. Okay? So the limit of the function, of course, does not exist, but the reason is that when you take this limit, the value of the function becomes a smaller and a smaller, or approaches infinity values, smaller and smaller negative infinity values without any limit. It just becomes a smaller and smaller. -10 billion, -100 billion, -1 trillion, and so on and so forth. So it keeps getting smaller in the negative direction without any bound. Okay, so let's do another example. And I trust that if you guys have any questions, you will let me know. So here we want to find the limit of this function. So with this one, we note that we didn't have to simplify, right? But this one, right from the start, I haven't even finished this, but look at this. We can simplify this, right? We can factor things out. So we're going to have to do that. Then apply the limit. And then x squared minus 4x plus 4 as x approaches 2 from the left. And we want to answer that question. Well, so let's first simplify this before we apply the limit. So we have the limit as x approaches 2 from the left of x, let's factor the numerator, x times x minus 2 divided by, take a look at this. This is an easy factorization, right? X minus 2 squared. And of course, this x minus 2 and 1 of this x minus 2, because we have 2 of them being multiplied, so 1 of that with that cancel out, and we end up with the limit as x approaches 2 from the left of x divided by x minus 2. So we have simplified this original expression as much as possible. Now we can apply the limit. So let's do that. So we have, if you apply the limit up here, so the numerator becomes some positive value, right? Anything. This is approaching 2 from the left. So you might pick 1.999 and I might pick 1.9. Both of us would be correct. So it's approaching 2 from the left. Okay, so the numerator would be approach, or numerator approaches a positive value. Right? This is, I should say, numerator. And what happens in the denominator? What does the denominator approach when we plug in, when x approaches 2 from the left? So if this is 1.999, this value approaches it approaches 0, but from the negative side, right? So it approaches 0 as a negative value. So let's write that down. Negative numbers, and I should make a note that this is the denominator, so let me write that down. Well, I've already started this, so let me finish this one. Negative numbers approaching 0. Okay? You plug in anything here for x as a number that approaches 2 from the left. From the left, that would be 1.99, 1.9995, 1.9999995, and so on, right? But this denominator is approaching 0 as negative numbers. Okay, so now we have this numerator that is a much larger, I'm talking about relative to, it's a small positive number, but with regards to the negative denominator values that are approaching 0, the numerator is a much larger value. But the denominator is negative. So we're approaching negative infinity in this case. So negative in the whole function, that original function, approaches negative, or the limit of that does not exist. But why? Because the values of that function get closer and closer to smaller and smaller negative numbers. Okay, like that. I hope this is making sense. I know this doesn't involve numbers, but it's okay. It's a way of reasoning the limit, what happens to the limit of this function. So now let's consider another case of finding the limits. So here, when finding the limit, of a rational function as x approaches infinity or x approaching negative infinity. Okay, remember that this one was a constant, right? In this case, we looked at what happens when the limit is infinity, but because x approaching a constant value. But here, we're looking at the limit of a rational function as x approaches infinity. So we're going to look at techniques we can use to find such limits. So the first thing we want to do is divide that has the highest power. Remember in our discussion of polynomials back in Math 126 and even Math 124, we talked about the leading term, right? So this is kind of like that because it has to do with the leading term in the denominator, but it doesn't divide, make the division by the coefficient. It just takes the x variable in the highest power it has and divides each term in the rational expression by the x to the highest power shown in the denominator. And this is just a description of it, but once you see examples, you know exactly how this works. It's pretty straightforward. That has the highest power. Then, once you've done that, once you've made this division, then simplify the expression. Then simplify the expression. And finally, apply the limit. Okay, so let's see examples of this. So suppose we have this example where we want to find the limit of some function as x approaches positive infinity, and the function is 3x minus 2 over 2x plus 1, right? Pretty easy rational function. Now, if you look at the denominator, the highest x term is this one, right? X to first power. So we want to divide every term in this rational function by x. Not 2x, but just by x, and in the highest power it occurs in the denominator. in the denominator. In this case, it's x to the first power, right? So let's do that. So we have the limit as x approaches positive infinity of 3x divided by x, right, minus 2 divided by x, divided by 2x divided by x plus 1 divided by x. Now that we did that, we want to simplify. Very, very procedural. So the more practice you get with these, the better you will be at it. This is just a bunch of procedure, that's all. So we have the limit as x approaches infinity. Let's simplify. We get 3, right? X cancels out. We get 3 minus 2 over x divided by 2 plus 1 over x. So that fraction simplifies into that. Okay. Can we simplify this any further? No. So let's apply the limit now. When you do that, that means just substitute for x with infinity. So we get 3 minus 2 over infinity divided by 2 plus 1 over infinity. Right? So anything divided by infinity, it's 0, right? So we have 3 minus 0 divided by 2 plus 0, which means 3 over 2. So in this case, the limit of this function as x approaches infinity is in fact 3 over 2. Okay, pretty simple, isn't it? Once you know the procedure, these become very, very easy problems to solve. So let's do another example before we look at another case. Okay, so suppose we want to find the limit as x approaches negative infinity of this function, like that. Okay, so we have the, once again, note the highest power of x in the denominator. It's x to the 4, right? So now we want to divide each term in this rational function by x to the 4th. So limit as x approaches negative infinity, we have 1 divided by x to the 4th plus x to the 6th divided by x to the 4th divided by x to the 4 divided by x to the 4 plus 1 divided by x to the 4. So what's the next step? Do you remember? We need to simplify, right? Let's do that. So we have limit as x approaches negative infinity. That one we can't simplify. We can't do anything with that. So let's keep it like that. How about this? Can we simplify this? Of course we can. 6 minus 4, the bases are the same. So in this ratio, the powers get subtracted. So 6 minus 4 is 2. How about this? Can we simplify this? Absolutely. We get 1 plus 1 over x to the 4, which we cannot simplify any further. Okay, can we simplify this, the whole thing anymore? No. So what do we do next? Do you remember? We apply the limit. So just substitute negative infinity for x. Both of these powers are, all of these powers, all three are even. So it's just going to be infinity. So we have 1 over infinity plus infinity squared. Negative infinity squared is just infinity, right? So infinity divided by 1 plus 1 over infinity. So infinity to the 4th power is meaningless, right? Infinity to the 4th power is just infinity. Okay, so let's simplify. What do we get? 1 over infinity, or any number divided by infinity, is 0 plus infinity divided by 1 plus 1 over infinity, again 0, right? So what do we get? We get infinity divided by 1, which is infinity. So the limit, again, does not exist. But why does it not exist? Because the value of the function approaches or becomes larger and larger without any bound. So that's why. Okay, so let's look at a case where we have to find the limit of an expression that is not a rational function as x approaches either positive infinity or negative infinity. That is not a, let me underline that, not a rational function. As x approaches infinity or x approaches negative infinity. All right, so let's show or discuss some techniques for this. So the first thing we want to do is factor out the expression if possible, and then apply the limit. So that's the only thing we have to do with those that are not a rational function. So first thing, factor the expression if possible of course, if possible. Then apply the limit to each factor. To see in which way to see to what value they approach. Okay, so that's basically a description of the technique. And as before, once we do some examples, you'll see exactly how this is done. So suppose we want to find the limit as x approaches infinity of this expression. Okay, suppose we want to do that. Okay, can we factor this? Absolutely we can. We can factor, in this case, we can factor out the lowest power of x. In this case, this is power, this x has power 1, this one has power 1/2, right? So we can factor out square root of x. So limit as x approaches infinity of square root of x factored out. So what do we get? We get square root of x minus 1, right? That's what we get. Now that we've factored out this expression, let's see how each factor behaves as x approaches infinity. So let's look at this piece first. So this piece and then this piece. Right. So this piece, as x approaches infinity, for sure the square root of x also approaches infinity, right? Square root of x approaches infinity as well. You take the square root of infinity, what do you get? Infinity again. So how about this one? More or less the same thing. As x approaches infinity, then this whole thing, square root of x minus 1, approaches infinity, right? You have infinity. Take the square root of it and subtract 1 from it. What do you get? Infinity, right? Because infinity is not a number. It's just enormously, infinitely large value. So large that we cannot put a bound or limit to it. So you take the square root of that, subtract 1 from it, you're still going to get infinity. All right. So we took we factored out this expression. We looked at the behavior of each factor as x goes to infinity, and in both cases, it's each factor approaches infinity. Therefore, the limit of the original function, the limit of that is infinity. And I'm sure you saw that ahead of me. So, so as x approaches infinity, that's equal to infinity. I cannot remind you enough number of times, this is not a limit. Limit does not exist. The limit of this function does not exist. But this is a way of showing with notation why it does not exist. It does not exist because the value of the function grow larger and larger without bound, okay? So this is not a limit, or the limit does not exist in this case. Let's do another example. Suppose we want to find this limit, the limit as x approaches negative infinity of x to the 4th plus x to the 5th and question mark, right? So can we factor this? Absolutely we can. In the previous one, we factored the x term with the lowest power Can we factor out the x term with the highest power? Absolutely we can. Okay, so let's do that. But we should factor, that's the main point. When you get an expression like that, we need to factor, then apply the limit to each factor to see how they behave. Each factor behaves. So limit of x approaching negative infinity. Let's take the largest power here as a factor. So x to the fifth. Then what do we get here? We must have x 1 over x, right? So x to the fifth times 1 over x, we get x to the fourth power back. And of course, plus 1. Okay? So once again, let's look at this piece, the behavior of this piece and this piece as x approaches negative infinity. So in this case, for this factor, because that power is odd, right? So as x approaches negative infinity, this whole thing approaches negative infinity because the power is odd. So as x approaches negative infinity, x to the fifth power approaches negative infinity as well. So how about this one? Well, once again, here we have as x approaches negative infinity, it's interesting because this piece approaches 0, right? It approaches 0 from the negative side, or negative values that approach 0. So minus 0.00001, minus 0.000000002, like that, okay? But it approaches 0. Once that happens, this whole quantity becomes 0 plus 1 approaches 1, right? So let's write that. As x approaches negative infinity, this whole thing, let me put it in parentheses, 1 over x plus 1 approaches 1, right? Because this term approaches 0, and 0 plus 1 means this whole thing approaches 1, which is what we have here. Okay, so you have basically one factor approaching 1 and another factor approaching negative infinity. So the whole thing approaches negative infinity. So therefore, we have the limit of the original expression, which was x to the fourth plus x to the fifth, as x approaches negative infinity, is equal to negative infinity. So this is not a limit, but the value of this function gets smaller and smaller, to become smaller and smaller negative numbers as x approaches negative infinity. Okay, so let's look at another case that we might encounter. So finding the limit of an expression that is not a rational function again, but it contains a radical expression. So far we haven't seen any of those yet, right? So we're going to look at those right now. And once again, let me underline this. That is not a rational function. But it contains a radical expression, or a root expression, right? Like that. So what do we do now? That's what we're going to talk about, the technique to use when this is the situation. Okay. So the first thing we want to do is rationalize the radical expression. So first, rationalize the expression. By multiplying it by its conjugate. We did this in college algebra math 124 and in pre-calculus math 126, and I suspect even in math 127 we did some of this, right? By its conjugate, and then simplify the product, and finally apply the limit. Okay, we're going to do that. So let's jump to an example of this kind. Suppose we want to find the limit as x approaches infinity of this function or expression, square root of 9x squared plus x minus 3x. And of course, minus 3x is outside of this radical expression. So this isn't a rational function, but it is an expression with a radical expression in it. So the first thing we want to do, as this description is indicating, is rationalize the expression. So let's do that. I don't know if the blank space I have is enough for me to fit all the solution. And the reason for that is that I want to list every step. I don't want to skip any steps. So let's see if I can fit it all on this page. So first we take the limit as x approaches infinity of that square root of 9x squared plus x minus 3x times square root of 9x squared plus x plus 3x divided by the same thing, right? 9x squared plus x plus 3x, close bracket. Okay, so what do we have? Then we have, let's multiply these. So limit as x goes to infinity of square root of all of this, 9x squared plus x minus 3x times all of that, square root of 9x squared plus x plus 3x divided by all of this. Plus 3x. Okay? So we know what happens here, right? We learned that from college algebra and pre-calculus 1. Okay, so recall from previous two classes that when you have x minus y times x plus y, do you remember what happens, which is the case we have? All of this is x, all of that is y. all of that x and all of that y. So we get x squared minus y squared. Remember that? So the same thing is going to happen here. We're going to have the limit as x goes to infinity of, so it would be square root of 9x squared plus x, right, squared, minus 3x squared. All of that divided by this denominator. So square root of 9x squared plus x plus 3x. Okay? All right. So let's simplify this. We have the limit as x goes to infinity. This power will cancel this radical expression. So we get 9x squared plus x. On this side, we get minus 9x squared. All of that divided by the same denominator. 9x squared plus x plus 3x. And of course, you can see right away that 9x squared and minus 9x squared add up to 0. So in the numerator, we get the limit as x approaches infinity of x divided by square root of 9x squared plus x plus 3x. Okay, I can move up to this portion of the space. I can move up and put really small but fill this space to keep all the solution on one page. But I don't know if that would make the page too crowded or what, but I think it would make it too crowded. So I'd rather go to the next page. I hope when you read over these lecture notes on your own, that I'd rather put the solution on one page, but in this case, it would make the page really, really crowded. So let me go to the next page. So now, after rationalizing what we had, we ended up with a rational expression, right? With x approaching infinity. So we end up, in this case, let me find that slide. Let me bring it back. This one. On page 4, what did we have? Finding the limit of a rational function as x approaches infinity or negative infinity. What did we have to do? We had to first divide each term in the rational function by the variable in the denominator that has the highest power, then simplify the expression and finally apply the limit. So after rationalizing this original expression that we had with a radical expression in it, we ended up with a rational expression as x goes to infinity. So we need to divide every term in this expression by the highest, by the x term with the highest power. So the x term with the highest power is just x, right? Because if you apply the square root to this 9x squared, you still get x. So x to the first power is the highest power of x that happens in the denominator. So let me write this down. Divide, let me move this down a little bit. So divide each term by the x term with the highest power. Remember, you don't have to divide by the coefficient. So just the x to the highest power it appears. So with the highest power in the denominator. Okay, let's do that. So we're going to have like that. Okay, so we have the limit as x approaches infinity of x divided by x. Inside the radical, when we divide the terms inside the radical by x to first power, we have to divide by x squared, right? Because square root of x squared is x. So out here, when we divide by x, it's just x. But when we're dividing the terms under the radical expression, we should then accommodate the index here. In this case, it's a square root, so we would divide by x squared on the inside of the radical, not outside. So if the index was 3, what would we do? We would divide by x cubed. If the index is 4, what would we do? We would divide by x to the 4th, and so on. Okay, so let's do that. So we have square root of 9x squared divided by x squared plus x divided by x squared. Now, 3x is outside of the radical, so we again divide by x, just like we did in the numerator. Okay, so now we can simplify this expression. So we have the limit as x approaches infinity of x over x is 1 divided by, what do we have on the inside? X squared and x squared cancel out. We get 9 plus 1 over x plus, of course, 3. Can we simplify these terms any further? No. So what do? We apply the limit. So we have 1 over square root of 9 plus 1 over infinity plus 3. Okay. So then let's simplify this. This would be 0. 1 over square root of 9 plus 0 plus 3. And of course, this would be, this whole thing is just square root of 9, which is 3. So 1 over 3 plus 3, or 1 over 6. Okay? So the limit of that original expression, that one, which was not a rational function, but it had a radical expression in it, is equal to 1 over 6. So the limit does exist, and it's equal to 1 over 6. Okay, so let's... so this example leads to an important result. Let me I think it's better if I put it right underneath it. So the previous example leads to an important result here, which is called limits at infinity. And that it says that if limits at infinity exist, then limit as x goes to infinity of f of x, let's say if it exists, then let's take it as a general value L. L can be anything, but the assumption is that the limit exists at infinity. So we can take that to be anything. And the limit, of course, from the negative side, negative infinity. So the limit of f of x as x approaches negative infinity is also equal to L. So if the limit of a function as x approaches infinity exists, then that it means, what does it mean? It means this, that the limit of that function as x approaches infinity and as x approaches negative infinity is equal to the same value, L. Okay, so this is an important result. Let me actually highlight it here. Like that. All right, so have that. So let's look at this result also graphically. And this is neat and quick, but it's still, it involves graphs, which is different than the numbers we've been solving. So it's a slight change from numerical to graphical interpretations. So I think it would be a nice, quick change for the next 5-6 minutes at least. So suppose we have this example where we want to use the following graph. For a function g of x, using the following graph for a function, let's answer the questions below. Okay, and here's the graph. Let's quickly draw that. So we have this x, and then we have y, and we have several asymptotes. We have two horizontal asymptotes, one at y equals -1. So let's draw that here. So this is y equals -1, and then we have another asymptote, or horizontal asymptote, at y equals 2 here, let's say. And we have a vertical asymptote at x equals 2. Let's draw that here. Maybe here, like that. So this is x equals 2. Okay. All right. So the graph that we have is as follows, and let me maybe use my thicker marker if I brought it with me. Yes, I did. So we have one graph that does, one piece of the graph that does this. Like that on this side, and like that on this side. And we have another piece of the graph that does this. Like that. And like this on this side. And also we have another piece of the graph that does this. Comes up here, comes that down, and then does that. Like that. like that. So you can see the asymptotic behavior at these endpoints. Okay, so the questions for us to answer, given this graph, are as follows. For part A, we want to know what is the limit of the function g of x as x approaches infinity. Okay, so that's the question mark. Well, as x approaches infinity, are we talking about this piece? No, right? X here varies between 0 and 2. So that's not the piece. Are we talking about this piece? No. This side, x approaching negative infinity, not positive infinity. On this side, x is approaching 0. So it's this piece. What happens at x approaches infinity? Is that this one? No. That x is approaching 2 from the right. So x is approaching infinity on this side. So what is the value of the function? What is the value of the function which is represented by this graph? What is the value of that function approached to as x goes to or approaches infinity? It's approaching y equals 2. So let's put that here. Okay, so for part B, we want to find the limit as x goes to negative infinity this time of function g of x. So that's the question mark. So that can't be that piece. It can't be that piece. It's definitely this piece, right? Because as x approaches negative infinity, that's the piece we're talking about. So as x approaches negative infinity here, what does the value of the function approach? It approaches y equals -1. That asymptote, right? It approaches it. The way it looks, horizontal asymptotes, as you know, can be crossed, not vertical asymptotes, right? Remember that? So as the way this has been drawn, the assumption, it looks like that it's not going to cross it here, but it crossed it here. But maybe not again. So after that, it just gets closer and closer to it, but it will not cross it. Okay, so part C, we want to know the limit of function g of x as x approaches 0. Okay, so let's look at the graph. Does x approach 0 here? No, x is approaching 2 there. And so is the case here. So where is x approaching 0? Right there. On both sides, in fact, as x approaches 0 from right and left, the function gets smaller and smaller and smaller in the negative direction. So we have the function value approaches negative, as you can see here, negative infinity. Okay, like that. So then, what about, let's say case part D, we want to find the limit of function g of x as x approaches 2 from the left. Okay, maybe I should move this up a little bit, like that. So x equals 2 is here, that vertical asymptote. From the left, we're talking about this piece, right? X is approaching 2 from the left, right here. So what is it equal to? It's approaching, the function value approaches negative infinity. In other words, it doesn't exist. So the limit here doesn't exist, but here it's -1 and there it's 2. Okay, remember this is that notation that tells us that the limit does not exist. Okay, this is the last one for the graph. So we want to know the limit of the function g of x as x approaches 2, guess what? From the right. Okay? So this is x, this vertical asymptote is at x equals 2. So from the right, is that this? No, that's from the left. So where is from the right? From the right is right here. This line of the graph, or this piece of the graph, approaches x equals 2 from the right. So what happens to the value of the function, which is shown by this thick blue line? It is going towards positive infinity. Like that. Okay? So, let's now talk about other techniques. There are other techniques that your book talks about that are very, very critical in problem solving in all your calculus classes. So let's also mention those and maybe do a couple examples on those techniques as well. So we have other techniques. Other techniques for finding the limit as x approaches infinity. Okay, so let me put in parentheses using, so in this particular case, we're using, or in this particular examples that we have, we're going to be using the squeeze theorem, and or the substitution method. We use the substitution method in Math 126 especially when we were converting equations of, when we were solving equations of higher power to a quadratic function. Remember that? When we substituted another variable for x squared, and we converted the higher degree polynomial function to a quadratic function, and we were able to solve the function that way. So this is kind of like that, but it's not the way, the purpose for which we applied it's not that, but nonetheless it's just introducing a variable as a substitution, and it's very useful, as you'll see. So let's just jump into one example right away. Suppose we want to find the limit of sine squared x divided by x squared as x approaches infinity. Okay. Well, first of all, we know that from Math 127, from trigonometry, how sine of x behaves, right? It oscillates between 1 and -1. Remember that? So let's make use of that, what we already know. So sine of x varies between -1 and 1. That's the range for the basic sine function. Okay, we remember that from trigonometry. So what happens if we square this? So therefore, or thus, if you square all these sides, you get sine squared x, and then the sine squared of x varies from 0 to 1, right? If you, within this range, if you square the values, what are you going to get? You're going to get 0 to 1, right? Because 0 is in the middle. 0 is between -1 and 1, so you square that, you get 0. -1 is going to drop out because all the negative values are going to drop out and become their equivalent positive values. So the sine squared of x will vary between 0 and 1. Now, in the original function, we had sine squared of x divided by x squared. So let's divide all three sides by x squared. Okay. So dividing by x squared, what do we have? We have 0 over x squared sine squared x divided by x squared less than or equal to 1 over x squared. Okay, so let's simplify this a little bit, right? We can simplify the left side only. So simplifying, we have on the left, we have 0. In the middle, we can't do anything right now, so sine squared x divided by x squared. Neither can we do anything in the right-hand side, so 1 over x squared. Okay, so now let's apply the limit to the whole thing. So taking the limit, right? We're going to have limit of 0, taking the limit, by the way, of everything as x approaches infinity. So let me add that too, as x approaches infinity, because that's what we have. That's what we have. So we're going to take the limit of everything we have as x approaches infinity, limit of 0 as x approaches infinity, less than or equal to limit as x approaches infinity of sine squared x over x squared, and then the limit of x approaches infinity, 1 over x squared. Okay? All right, so on the left, we earlier in the previous sections, we learned that limit of a constant at any value is just equal to the constant. And doesn't matter if x is approaching infinity. So the left side is still equal to 0. The middle we're still trying to figure out, so let's keep it. Limit of sine squared x divided by x squared as x goes to infinity. And earlier we had a theorem. Let me bring that back to show you. It was a very useful theorem. It was on one of these previous slides. I'm going to find it in a moment. Let's see. Which says that value is equal to 0. I just want to show you that if I can find it. Looks like it's okay. It was on one of these pages. Let's see. I don't seem to find it right now. But we had a theorem that said that if this n is a positive integer, then as x goes to infinity, that term approaches 0. And it should be here. I don't know why I can't find it. Let's see. It was on one of these pages. Okay, so it's not. Okay, so it's not here. Maybe I should then put it on one of these sheets. But this right-hand side, it goes to 0. So you have a limit of an expression on either side, the terms approach 0. So by the squeeze theorem, the middle part should also approach 0. So by the squeeze theorem, we have the limit of sine squared of x divided by x squared as x goes to infinity is also equal to 0. Okay, so maybe I can find it in my notes here. One second as I search for this. Let's see. If it's not there, then I must have. But it's in your book. It's a little theorem. And so. Oh, it's coming up, so that's why I can't find it. So right after this example, we should mention a very important theorem. Sorry for that, but it's coming up right now. So this is the theorem I was talking about. I thought I had covered it, but apparently not. So note, this is a very important note. That if n is a positive integer, then the limit of 1 over x to n power. In this case, in the example that we just went over, n is 2, right? But n can be any positive integer. As x goes to infinity is equal to 0. And this is the same thing. This is true even if x approaches negative infinity. Limit of 1 over x to the n power as x approaches negative infinity is also equal to 0. So let me highlight this as one of the. As you can see, that's a very easy theorem to remember or note to remember, but it's very useful, as it was in this case when we applied the squeeze theorem, right? So easy but useful theorem. Okay, so let's see another example. In this case, we're going to apply the substitution method. So suppose we want to find this limit, the limit as x goes to infinity of x times sine of 1 over x. Okay. Okay, so first of all, you've seen this before, that we have an axiom or a theorem that says that, so let's recall this one. Recall that the limit of sine of x divided by x as x goes to 0, not infinity, as x goes to 0, of sine of x over x is equal to, do you remember what it is equal to? 1, right? We've seen this before. Now, look at this and take a look at this. Maybe we can rewrite this in this form using a new variable or substitution method. We might be able to do it, but at least if you remember this theorem, then this, when you look at this problem, it should give you a hint that maybe you can use this to solve this, to answer this limit problem. So let's see how we can do that. So let's say that using the substitution method. So this is our intent. Using the substitution method, let us try to write the original problem or the original function, that one, the original function as x approaches infinity in terms of a new variable approaching 0. Because if we could do that, then maybe we can use this to help us solve that limit question. Okay, so in order to do that, let us take t, variable t, equaling 1 over x. Okay, so we're going to use substitution. We're going to introduce a new variable to apply the substitution method. So let's take a new variable t being equal to be equal to 1 over x. So what does this mean in terms of x? Because we still need to know what x is, right? T, we're taking it as 1 over x. So what is x? Okay, let's find that out. Therefore, x is simply 1 over t. And then so now we know what x is. We know what 1 over x is, and we know what x is, right? 1 over, but what about the limit? The limit can stay as x goes to infinity, right? That was the limit of x. So what happens to the limit of t, right? So as x goes to infinity, here, what happens to the limit of t? T goes to 0, right? So therefore, as x goes to infinity, t goes to 0 from the, because 0 is in between, as you know, it's in between negative and positive values, right? So it's the only number that's like that. So it's important for us to determine now whether we're approaching 0 from the left, which it would mean we were in the negative value region, or from the right, which would mean we are in the positive values region. So this, in this case, positive infinity, so this would be coming or approaching 0 from the right side. So t is approaching 0 from the right. Okay, so we're in the positive values region. Okay, so now, given the t as a new variable that represents 1 over x, right? So this is the critical step we're taking here. Let t equals 1 over x. Let's rewrite let's use this new parameter to rewrite the original expression. So use the new parameter or variable, the new variable t, to rewrite the original expression. Okay, so let's do that. So instead we have the limit. We no longer have x going to infinity. Instead, what do we have? As x goes to infinity, t goes to 0 from the right-hand side. Then x, we don't have x. What do we have instead? We have 1 over t. 1 over t. We no longer have sine of 1 over x. We have sine of t, right? Because t is equal to 1 over x. So sine of t. So as you can see, I'm sure, this is equal to, let's rewrite this, right? So limit of t as t approaches 0 from the right of sine of t, multiply this over t. So we know that useful axiom, right? Limit of sine of x over x as x approaches 0 is equal to 1. So by the same token, sine of t, limit of sine of t over t as t approaches 0 is equal to 1. Like that. So this technique, substitution technique, proves to be very useful in this case. So I'm happy that you stuck around all the way through to the end of this video. Please don't hesitate to rewatch these videos again and again until things begin to sink in. Read your book. Your book is an excellent book. The author, Stewart, explained things very clearly and very well with lots of examples. And so for now, have a nice day, and I'll see you again next time.